Imagine spending like months meticulously cultivating a rare tropical plant, you know?
Yeah, getting the soil composition just right.
Right. You're nursing it through the changing seasons. You finally see it thrive. And then, bam.
The weather happens.
Exactly. You wake up after a passing storm to find it just completely shattered across your patio.
It's the worst feeling. Dirt is everywhere.
Everywhere. The delicate root system is exposed to the harsh sun. And, I mean, the leaves are totally crushed under the weight of its own container.
Yeah.
So today's deep dive is really about what happens when gardening stops being this relaxing weekend hobby and turns into, well, literal structural warfare against the wind.
It is a phenomenal case study in everyday engineering, to be honest.
It really is.
Because what we are looking at today is a raw, totally unfiltered account of human ingenuity being forced into action by environmental chaos.
Yeah.
It's basically a masterclass in breaking a problem down to its bare physical components.
So our source material today is a first-hand account. It's an entry simply titled Notes on Gardening, Part 948.
Part 948.
Right. Written by an author named Ang and published on July 7th, 2026. And the detail that jumps out immediately is, like we just said, that number, Part 948.
It tells you everything you need to know about the mindset we are examining here.
Definitely. We are dealing with someone who has been iterating, observing, collecting empirical data, and documenting their struggle for a really, really long time.
Because gardening in this context, it isn't a static painting you just hang on a wall.
No.
It is a highly dynamic, actually very hostile environment. Ang is meticulously documenting the brutal realities of tropical weather.
And the main villain in this story.
Aggressive, high-velocity wind. The source notes detail numerous instances where these tall, potted plants are systematically being knocked over and destroyed by lateral gusts.
Okay, let's unpack this. We have a gardener, we have aggressive tropical winds, and we have a patio full of plants continually taking a dive.
Right.
But reading through Ang's observations, it becomes very clear this isn't just like a string of bad luck.
No, not at all.
We are looking at a fundamental engineering failure.
Exactly. The root of the issue actually starts below the soil line.
Oh, interesting.
Yeah, to understand the vulnerability, you really have to look at the biological requirements of a tropical plant.
So what are they on?
Well, a tropical environment means heavy, sudden downpours. To survive that without the roots rotting, the plant requires a high drainage potting mix.
Which means water has to flow through it fast.
Very fast. By definition, a high drainage mix is extremely porous.
Like chunky.
Yeah, it's composed of materials like perlite, coarse bark, and mostly, well, empty space.
Just air pockets.
Right, air pockets that allow water to flush through rapidly.
Meaning you are intentionally creating this feather-light base.
Exactly.
There is virtually no mass anchoring the bottom of the pot.
And growing out of that feather-light aerated base is a tall tropical plant.
Right, which keeps growing.
Over time, as the plant grows and adds foliage, the center of mass continuously shifts higher and higher.
So it's top-heavy.
Incredibly top-heavy. The structure becomes inherently unstable.
And then you put that into a normal pot.
Yeah, when you place a tall, top-heavy system into a standard plastic nursery pot, you have engineered a highly unstable system.
Because of the shape of the pot, right?
Yes. Standard nursery pots usually taper down to a very narrow footprint at the bottom.
It's basically like a person balancing on their tiptoes while holding a giant umbrella in a hurricane.
That is a perfect way to picture it.
Of course they're going to tip over.
Oh.
I mean, it's a classic lever problem.
Yeah.
The tall plant is essentially a giant crowbar.
Yep.
The tropical wind is the hand pushing it, and that tiny tapered rim of the nursery pot acts as the perfect fulcrum to just pry the whole thing right out of the ground.
Exactly. The wind gets a massive mechanical advantage because of the height of the plant.
Right.
The physics are entirely stacked against the survival of the plant. The higher up the wind hits the broad leaves, the more rotational force, or torque, is applied to the base.
And because of the lightweight soil?
Because the soil is full of air pockets, the system completely lacks the necessary internal weight to counteract that rotational force.
It has no ballast.
Right, no ballast. The wind easily overcomes the minimal mass at the bottom, pivots the entire structure over that narrow fulcrum, and brings the whole thing crashing down.
So my immediate thought here is, why not just change the dirt? Like, why not just pack that pot with some dense, heavy clay soil?
It seems like the obvious fix.
Right. If the problem is a lack of ballast at the bottom of the lever, just anchor the whole thing down with heavy earth.
Well, this is where the environment dictates the botany. which in turn limits your engineering options.
Oh, because of the drainage.
Yes, if you use dense, heavy soil to weigh the pot down, you lose the drainage.
And you trap all that sudden tropical rainfall inside the container.
Exactly. The root system suffocates from a lack of oxygen, fungal rot sets in, and the plant dies.
Wow. So you'd be saving it from the wind just to drown it in the dirt.
Precisely. The soil is a fixed variable. The wind is a fixed variable.
You can't change either of them.
You cannot change the weather, and you cannot change the botanical needs of the root system.
So something else has to give.
Therefore, to prevent catastrophic structural failure, the architecture of the container itself must adapt.
Which brings us to the evolution of geometry.
Yes.
Because reading through Eng's notes, you get to see this relentless, iterative, problem-solving process play out.
It's fascinating.
Eng didn't just instantly arrive at a flawless design.
Yeah.
The initial attempt to fix the falling pots was actually very brute force.
Right. The notes describe an early strategy of migrating the plants into larger, slightly shorter pots and filling the bottom with heavy substrates.
Like what?
Think dense rocks, thick gravel, materials with high mass.
Basically trying to manually add back the weight that the high drainage mix took away.
Yeah, fighting the kinetic energy of the wind with sheer mass.
Does it work?
I mean, it is treating the symptom within the confines of traditional garden supplies. Lowering the center of mass and artificially introducing ballast does improve wind resistance slightly, but it is highly inefficient, and it adds unnecessary weight to something that might actually need to be moved.
Right, which we'll get into.
Then we see a radical shift in problem solving.
This is my favorite part.
Eng is out running errands far away from any gardening center and spots a plastic water basin.
Here's where it gets really interesting.
Yeah.
Eng looks at a basic water basin, like a laundry tub essentially, and completely strips away its intended purpose.
Yeah.
It is a brilliant example of overcoming functional fixedness.
Which is such a powerful cognitive block.
Totally. Functional fixedness being the cognitive bias that limits a person to using an object only in the way it is traditionally used. We see a basin and think water.
But Eng saw a basin and saw raw geometry.
Exactly. And stops looking at the aisles of the store as, predefined categories and starts looking at them as structural materials.
Right.
The notes specify that the basin had adequate height for a root system and a similar top circumference to a regular flower pot.
But the defining feature.
The game-changing feature was its massive untapered base.
What's fascinating here is the complete paradigm shift in the engineering approach.
How so?
Well, Eng moves from a weight-based solution, relying on heavy gravel for ballast, to a purely geometry-based solution.
Ah, I see.
Expanding the footprint of the container fundamentally alters the physics of the object in relation to the wind.
Because it stays wide all the way to the floor.
Yes.
It doesn't taper down to save space on a shipping pallet like a standard nursery pot.
Exactly. We talked about the fulcrum point earlier, that edge where the pot tips over.
Right.
With a wide water basin, if the lateral wind wants to apply torque and tip it over, it has to lift the plant's center of gravity over a significantly wider distance.
Oh, wow.
The fulcrum is moved far outward, away from the center of mass.
So the wind loses its mechanical advantage.
Entirely.
Going back to the crowbar analogy, the wider base essentially shortens the crowbar.
Yes.
The wind can push all it wants, but it doesn't have the leverage to pivot the structure over that extended edge.
The leverage is neutralized by geometry alone, entirely eliminating the need to haul heavy rocks to create artificial ballast.
It just sits there.
The structure becomes inherently stable just by changing its shape.
But wait, we have to address the obvious hurdle here.
The water problem?
Yes. A water basin is designed to hold water. That is its primary function.
Right.
Putting a delicate tropical plant in a watertight tub completely defeats the purpose of the high drainage soil we just established as a biological necessity.
It does.
If the water can't escape, the roots rot.
Well, a basin is not naturally a pot, which means to implement this geometric advantage, Eng had to physically cross the line from passive consumer to active modifier.
Oh, I love that phrasing.
The basin requires a critical adaptation to function in this new role.
It needs DIY surgery.
Exactly.
Eng details this really scrappy, hands-on method to repurpose the basin, mentioning that adding drainage holes to the bottom is easily achieved.
Right.
The notes suggest using an electric drill, or, alternatively, using heated metal to puncture the plastic.
And that mention of heated metal is particularly insightful from a material science perspective.
Oh, really? Why?
Because these inexpensive water basins are typically manufactured using amorphous polymers.
Amorphous polymers.
Yeah, relatively thin, somewhat brittle plastics designed to hold static water, not withstand mechanical stress.
Okay, so what happens if you drill it?
If you take a high-speed electric drill to that kind of plastic, especially without a solid backing block, you run a really high risk of tearing the material.
Oh, I've done that. It cracks.
Yes, you create microfractures radiating out from the drilled hole.
Which would compromise the whole structural integrity of the basin.
Exactly.
The moment the wind puts stress on the container, those microfractures could spiderweb and the whole bottom could blow out.
But melting the plastic with a hot skewer or a heated nail, however, cleanly displaces the material.
And melts it away.
Right. The heat effectively cauterizes the edge of the new drainage hole, leaving a smooth rim that prevents those stress concentrations and microfractures from forming.
That is so smart.
It is a highly durable, localized field modification that actually preserves the strength of the plastic.
I love that level of practical resourcefulness.
It's brilliant.
But it does lead me to a bigger question.
Okay.
Why go through all this trouble? I mean, why wander through the home goods aisle, evaluating the geometry of laundry tubs, and then take a hot piece of metal to melt holes in them?
Fair question.
Because, there's an entire category of premium gardening pots that are already designed to be incredibly heavy and wide at the bottom.
Yeah.
Think of glazed ceramic pots. They already have drainage holes, they have massive wide bases, and they weigh an absolute ton.
It is the most obvious alternative, and to be honest, it is a solution that many amateur gardeners would just default to.
Right.
Eng actually addresses glazed ceramic pots directly in the notes.
Oh, so why rule out the premium ready-made option? Let me think about this.
Think about the environment.
Earlier, you made a point about the garden not being a static painting.
Right.
It's a dynamic environment. Eng is constantly observing, iterating, and reacting to the weather.
Constantly.
If you are tracking seasonal sunlight or trying to drag a collection of plants under an awning to survive a severe monsoon,
Exactly.
trying to hustle a 50-pound ceramic fortress across a wet patio, sounds like a logistical nightmare.
The notes explicitly reject glazed ceramic for that exact reason, revealing this really deep, practical understanding of day-to-day garden maintenance.
It's just too heavy.
Well, first, ceramic is expensive, which is a significant barrier if you are outfitting an entire patio of vulnerable plants.
True.
But the mobility aspect is the ultimate deal breaker.
The heavy ceramic definitely anchors the plant against the wind, but it completely traps the gardener.
That's a great way to put it. Eng needed a solution that provided uncompromising geometric stability against lateral wind force, but remained lightweight enough for a single human being to easily pick up and relocate on short notice.
And the plastic basin does that.
The modified plastic basin achieves this perfect equilibrium. It provides the wide fulcrum to defeat the wind while utilizing the lightweight nature of thin plastic to preserve the gardener's mobility.
So what does this all mean?
Well,
it means Eng applied pure first principles thinking to realize that the quote-unquote premium solution, the expensive glazed ceramic pot sitting in the boutique garden center, is actually a trap.
It really is.
It solves the wind problem by creating a severe maintenance problem.
Exactly.
The true optimal tool for the job, the most elegant engineering solution, is a cheap plastic laundry tub and a hot nail.
It strips away the marketing of what a flower pot should look like and asks only what the structure actually needs to do.
Form follows function.
Right. It needs to hold high drainage soil, it needs to release water, it needs to resist lateral torque, and it needs to be carried.
And the basin does all of that.
The modified basin hits every single metric flawlessly.
And it really shows the value of stepping outside the designated aisle when you are trying to solve a problem.
Definitely.
If you only look for solutions in the gardening section, you are only going to find the flaws and limitations of the gardening section.
And so true.
The built environment around us is just raw material waiting to be repurposed, provided you actually understand the physics of the problem you are trying to solve.
That is the core takeaway. When faced with environmental chaos, you don't fight the elements with brute force.
No.
You analyze the mechanics of the failure, and you alter the geometry of your system to neutralize the threat.
And that brings us to the end of today's deep dive.
It's been a fun one.
We've taken you from a frustrating scene of shattered plants and exposed roots all the way to a brilliant exercise in first principles engineering and geometric problem solving.
Yeah.
Eng's note, and remember, this was part 948 of their documentation, highlights the relentless, iterative nature of practical work.
You can't just fix it once.
Right? You don't just solve a dynamic, hostile environment once. You continuously adapt your systems to it.
Because adaptation is the only sustainable strategy in a system that is constantly subjected to external stress.
Well said. As we wrap up today, we want to leave you with a final thought to mull over.
Okay.
Think about the incredible irony of that high-drainage potting mix we spent so much time discussing today.
The chunky, airy dirt.
Yes, the very thing the plant absolutely needs to survive its wet tropical environment, that fast-draining, highly porous, airy soil, is the exact same thing that makes its foundation feather-light, top-heavy, and completely vulnerable to being destroyed by the tropical wind.
The biological survival mechanism is the exact source of the structural vulnerability.
It makes you wonder, how often in our own lives or in the complex systems we build for our work are the very solutions we implement to keep things healthy and functioning simultaneously, creating the invisible vulnerabilities that will completely knock them over in the next storm.
That is a great question to ask.
Keep that in mind the next time you're troubleshooting a failing system.
Mm-hmm.
Thank you so much for joining us on this deep dive.
Thank you for listening.